Let's jump right into this explainer and tackle an absolute mathematical monster, the seriously complex dynamics of 3D rotation. We're going to take a trip from the messy, physical world we can actually touch, straight into the beautifully abstract mathematical toolkits physicists use to decode the universe.
Now, you might look at a simple spinning top and think, hey, that's just a childhood toy. But mathematically, it is a chaotic puzzle that has literally challenged the greatest minds in classical mechanics. When this thing spins, it's not just moving in one simple circle. It wobbles, it tilts, it drifts. Tracking that motion mathematically turns into an absolute nightmare of constantly changing variables.
And that brings us to our anchor for today, a heavy symmetric top. You can see how gravity is pulling down on its center of mass, while that pivot point on the ground forces it to stay put. Because it's symmetric, its principal moments of inertia along two of its axes are perfectly equal. This symmetry is basically our only lifeline for solving its motion. But even with that, we're going to need some incredibly heavy-hitting math to figure this out.
So, here's our roadmap for the explainer. We'll start with the spinning top problem, decode Euler's angles, crack open Euler's equations, unpack the Hamiltonian toolkit, and finally wrap up with symmetry and Noether's theorem.
Let's kick things off with part 1, the spinning top problem.
The real kicker here is that, unlike a train moving along a nice, straight track, a top's coordinate system is spinning right along with it. To actually calculate the top's angular momentum, we have to use what's called a body-fixed axis system. Think about it. If we measure from the fixed room we're standing in, the top's moment of inertia is constantly changing as it flips and wobbles around. But if we attach our axes directly to the top itself, that moment of inertia stays beautifully constant. The catch? Our coordinate system is now spinning, which introduces a whole bunch of fictitious forces and some seriously intense rotational cross products.
Moving on to part 2, decoding Euler's angles. To make sense of this tangled mess, we can break down any 3D rotation into 3 highly specific, measurable angles. Instead of a horrifying matrix of coordinates, Euler gave us this incredibly elegant sequence: spin, precession, and nutation. Spin, which we denote with the Greek letter psi, is just the top spinning around its own symmetry axis. Precession, or phi, is the top's axis sweeping around the vertical axis of the room. And finally, nutation, theta, is that nodding up and down tilt angle.
Now, visualizing these all at once is notoriously tricky, but it helps to look at the line of nodes. That's the intersection of the horizontal plane of the fixed room and the tilted plane of the spinning top. You can see exactly how the spin, precession, and nutation axes all interlock here. By tracking how these 3 specific angles change over time, we can pinpoint the exact orientation of our top down to the millisecond.
All right, let's get into the math. Part 3, inside Euler's equations.
Just take a look at how these variables, like the angular velocities, are squared and multiplied together. That intense nonlinearity is exactly why finding a general solution to this problem is basically impossible. Look at the equation for torque around the x-axis. You've got the notation acceleration, that theta double prime, matched up with the square of the precession velocity, and then multiplied by the sine and cosine of the tilt angle. You absolutely cannot just combine elementary solutions to solve this. It's incredibly coupled and highly nonlinear.
But watch what happens when we apply some special constraints. Let's look at steady gyroscopic precession, where the nutation angle remains totally constant. This lets us simplify those monstrous equations big time. If the top isn't nodding up and down, meaning our angle theta is locked in as a constant, then its derivatives completely vanish. We just turned a chaotic, unsolvable mess into a highly stable, steady precession, where the top just smoothly sweeps out a cone shape. By the way, this exact principle is how gyroscopes maintain their incredible stability in spacecraft and airplanes.
That brings us to part 4, the Hamiltonian toolkit. Because Euler's equations are such a beast to solve directly, physicists had to get creative. We can transition from the Lagrangian approach, which focuses heavily on velocities, over to the Hamiltonian approach. Here, we analyze generalized coordinates, labeled q, right alongside their canonical momenta, labeled p, on a completely equal footing. We treat them as independent, equal variables. This opens up a vast, multidimensional geometric space called phase space. And in this phase space, the rules of physics take on a totally beautiful, almost magical geometry.
Inside this new space, we can leverage Lie algebra tools, like the Poisson bracket, to easily test if a component of our spinning top's angular momentum is conserved over time. This bracket is an incredibly powerful algebraic structure. If you take any property of your top, let's say its angular momentum, and plug it into a Poisson bracket with the Hamiltonian, which represents the total energy of the system, the output tells you exactly how that property changes over time. If the bracket equals 0, boom, you've just found a constant of motion, meaning that property is strictly conserved. To solve the absolute hardest problems, we use canonical transformations to completely swap out our coordinates while still preserving Hamilton's equations. We use these 4 categories of generating functions almost like mathematical magic tricks. If a problem is just too nasty in your current phase space, you just morph the space itself. You invent completely new coordinates, capital Q and capital P, where the new momenta are perfectly constant, which suddenly makes the problem trivial to solve. These generating functions, F1 through F4, are literally the bridge between your old chaotic world and a newly designed, perfectly ordered mathematical world.
And finally, Part 5, Symmetry and Noether's Theorem.
For every continuous symmetry, there corresponds a conserved quantity. Noether's brilliant theorem reveals that the stability of our physical world isn't just random luck. It's dictated by the fundamental symmetries of the universe itself. This is arguably one of the most profoundly beautiful insights in all of physics. It tells us that conservation laws aren't just arbitrary rules made up by scientists. They are the direct, unavoidable mathematical consequence of the universe possessing symmetry.
So when you think about it, the reason our symmetric top doesn't just instantly fall over is deeply tied to the rotational invariance of space itself, the fact that the universe has no preferred direction. Because the laws of physics don't change if you rotate your experiment, which we call the isotropy of space, total angular momentum has to be conserved. Because the laws of physics don't change whether you run your experiment today or tomorrow, the homogeneity of time, total energy must be conserved. Your top stays upright literally because the very fabric of space is isotropic.
It really leaves you wondering, doesn't it? If shifting our perspective from moving axes to Hamiltonian phase spaces and universal symmetries can completely tame the mathematical monster of a spinning top, what other impossible physical mysteries are out there, just waiting to be solved simply by changing how we look at them? We just went from a simple childhood toy all the way to the deepest symmetries of the cosmos, entirely through the power of mathematical abstraction. And honestly, that is exactly what makes studying the mechanics of our universe so incredibly rewarding.